Anybody remind me what was the last thing we spoke about?
We talked about mixing colors and
Ah, yes.
why. Yeah.
Yep. Yep. Okay. So we talked about, oh, if you've ever painted before, um, there's a distinct difference between color palettes that are designed for digital display, online media versus physical media. Okay. And if anybody has ever painted before, if you mix the primary colors of red, green, and blue, technically, in theory, you should get black, but you don't. You get brown, right? You get kind of this mucky brown color, right? So for real world media, printed media, things of that nature, um, the CMYK standard was adopted or is used, where black is its own channel for this reason, because in situations of printing, um, of plotting, laying down, let's say, if you are making a wrap for a car, let's say, that's big nowadays, is people making a lot of money out of vinyl wraps for cars. Um, you want crisp black colors. The brownish doesn't work, right? So you'll notice that there's a clear distinction for digital displays and real world media like printed media and things of that nature. And they're virtually identical in the way that the colors function. They're just equally shifted into a different range of the color spectrum. And we'll talk about that here in a second. But you'll notice that almost every high quality printer is based upon the CMYK standard, where it'll either have a separate cyan, separate magenta, and separate yellow cartridge or channel, and a K cartridge or black cartridge. Higher quality printers even have a base tone or base color channel that is laid down for the other colors to interact with, kind of like a foundation. Um, so that's an important distinction to make. Uh, Also, efficiency wise, it's far more efficient to use one channel, one toner, one ink cartridge of black than to use three cartridges of red, green, and blue to make black, right? You're going to consume 3 times the liquid, the fluid, the toner making black, as opposed to having a dedicated black mixed beforehand. The benefits, there are multiple benefits in regard to why there's this channel distinction. Um, so that's why you'll encounter typically a separate black channel, separate black cartridge, because it's more efficient. You're not mixing 3 separate sources to make the color, and you get a better color. All right. So the most basic foundation of any type of digital display is the pixel, and the pixel is a physical point of reference on a raster image, the smallest addressable point on a display device. All right. Each dot on the display, depending on the color that is shown, the color that is activated and the light is shown through, that's the color that's generated, right? And then we can mix multiple shades, multiple color sources to generate the different colors that we want. Okay, so pixel is made up of a variation of 3 primary colors, and each pixel will have a unique physical coordinate, XY, on the screen. And that XY coordinate is important not only because of the location of what generates the actual image. When you start placing objects or editing things in, let's say, Premiere, if you're editing video, that XY location will be important because you will specify that XY location in the settings or the properties of an object that you're placing, or where a particular fade or transition is going to start from. In most cases, that XY location is the top left corner of the object or the asset, but it varies. But overwhelmingly, that XY coordinate that you'll see is the top left corner of the object or the asset. So for example, we were talking last class about the broadcast that the broadcaster was making. His, right, if we draw this quickly and crudely, annotations, there we go, right? So we had this basic layout. I don't want white though. We had this layout. Come on. What's going on here? Fail at first, try again. All right, so we had the entire display. This aspect ratio has become the standard now. Previously, we had a 4:3 aspect ratio. Now we've gone on to 16:9, 16:10, which is the relationship of the width versus the height. But the placement of assets on the eventual product or video that you're going to render is going to have an XY coordinate. All right, and then it's going to have a height and width property based off that XY. So it's going to have some XY location, and then based off of, let's put this in another place. Based off of that XY, you're going to have your height and width of the object or the asset in pixels, right? This will all be measured in pixels. The pixels is the common standard that you'll see across everything, right? So we have our XY. And then we have our height and width, okay? There's no circular measurements, right? There's no, you're not specifying, even if you have let's say the broadcaster was displaying their camera with a circle, for example. Let's choose a different color, right? They were displaying their webcam inside of a circle. That circle is still going to be based on some sort of height and width measurement. It's not going to have a radius and diameter. Okay. All right. So we can save that and clear it. So the pixel is the primary foundation, and we can calculate exactly how many pixels there are on the display based on the height and width or the resolution specification that a particular, in this case, video may have. Okay. So that leads me into pixel density. But before I move to pixel density, let's just really quickly talk about that height and width measurement, right? So 1080p, still the most prevalent standard. We are transitioning into 4K, but 1080p is still the most prevalent. We have our height and our width, and in the case, it's interesting how they kind of confuse you in that with 1080 they base the measurement off of one side, and with 4K they base the measurement off of another. So if we're talking about 1080, we're talking about 1080 pixels of height, right, in the display. And if we're talking about a 16:9 aspect ratio, okay, we say 16:9 aspect ratio, okay, then the complementary value of our width is 1920. Okay, right. And if we think about this, this is actually a grid that's occurring here, right, of pixels of, we have our, whoops, we have our vertical pixels along the width direction, and we have our horizontal pixels across the height measurement, right? And the cross product of the two, of the height and the width, gives us the total number of pixels inside of the display. So if we do the math, every 1080 display contains how many total pixels? If we do the cross product of the width times the height, what do we get? Roughly what? 2 million, 2.1, roughly 2.1 million, right? What's the, does somebody do the actual math? Right. Just shy of 2.1 million. 2.1 million pixels in a 1080 display. All right, so important, let's just get that out of the way so that you guys know what I'm talking about for the most part. Okay. All right, now the density becomes dependent upon the actual physical size of the display and how those 2 million pixels, we'll stick with 1080 for now. We can talk about 4K. We will talk about 4K in great detail as we continue. But the pixel density is the result of what the actual physical size of the display is and how those 2 million pixels are distributed across that physical size, right? So smaller physical displays will have what kind of pixel density? Higher density, absolutely, right? Because the smaller physical size, the net amount of pixels is unchanged in the display, but the smaller physical size means that the pixels have to be closer together, so the pixel density is higher, right? And if you're sitting in, let's say, one of the Javits lecture halls or something like that, and now you have this 100-inch display or 150-inch display, it probably, shoot, if I think about the display sizes, if I had to do a rough estimate, we would do probably 15 feet maybe across the diagonal, okay? And what do you immediately, if you've ever walked up to talk to the professor after class, what do you immediately notice on the display as you approach it? I'm assuming that you've all taken a class in one of the large lecture halls. That might not be the case for everyone, but as you approach a very large display that has a resolution of 1080, as you approach the large display, what does your eye begin to detect?
You can see the individual pixels. It gets blurred.
Right. Absolutely. You can start to see each one of the individual pixels. And if you get even closer, you start to see the individual color sources in the pixels, right? Because in the situation of, let's say, the projector display, the colors actually aren't physically overlaid one on top of the other, right? They're actually packed tightly next to each other, adjacent to each other, because at a certain distance, your eye will not be able to tell the difference, that there is a slightly off-center orientation of the different color sources, right? But it depends again on the quality of the display and what the display's use is. Okay, so the pixel density is the relationship between the area, the physical size of the display, versus the number of pixels that occupy that display. So 1080 is a static value of roughly 2.1 pixels, and then the display size dictates how tightly or how loosely packed those 2 million pixels are on the display. All right. So the higher the pixel density, the higher the quality of the displayed image. Why? Because your eye has a limit or a threshold where it can no longer detect the differences or the slight displacement of the individual colors and the individual pixels at a certain distance. So there is a ceiling where the human eye will no longer be able to detect increased densities. This is roughly about 720 pixels per inch, and that will be our standard measurement for pixel density will be either PPI or DPI. They're completely interchangeable, PPI and DPI, pixels per inch or dots per inch. Just DPI kind of evolved from a printing environment where you would have the drop of ink that would be placed versus a digital display where the pixel is placed. Okay. So it's roughly right around 720 pixels per inch at 1 foot of distance between the eye and the display. But anything beyond 300 PPI has very quickly diminishing returns, meaning that having that increased information, having that increased density does not have a linear relationship in how the quality will be perceived by your eye, right? So it'll taper off. So it won't be a linear relationship that says, okay, the higher, if we do this and okay. If we have per eye perceived quality versus pixel density. Okay, it's not a linear relationship. We have it has a quickly after this point here at 720 at 1 foot, it has diminishing returns. So it's more like this, right? Kind of like that. We'll reach a ceiling. It's probably even lower if we were to talk about it. All right. So most images or videos that will be displayed on smaller devices do not require a high pixel density, as high of a pixel density. Okay. Videos that are rendered for larger displays, banner displays, event halls, things like that, they require higher pixel density because the person will be able to get closer to the display and your eye will start to be able to detect the individual pixels that make up that image. All right. So there's definitely that distinction. Now, also just a note about real world objects or media versus digitally displayed media. In digital displayed media, the limiting factor is the display itself, right? The physical properties and specifications of the display. In the real world, right, the limiting factor is your eye. So in rendering and generating media for digital display, you have to keep in mind that there is a very pronounced bottleneck in the type of display that's being used, right? And that bottleneck is pretty consistent across pretty much all cases, right? But we do have to be mindful of pixel density versus physical display size. All right, so resolution, we talked about this already. I've already given you the crash course. But resolution is the measurement of the number of pixels in the horizontal and vertical directions of a display or image. And common resolution values 1080 and 720 and now 4K. Commercial cinematography typically measures it as 4096 by 2160 pixels, and consumer is right around 3840 by 2160. 1440 at what aspect ratio, Ryan? 16 by 9, 16 by 10. We have ultra wide screen, right? So you can do that calculation really easily if you want, right? If so, 1440 is going to be, right, 1440. That's going to be your vertical dimension, right? So if we divide 1440 by 9, what do we get? You can shrink this down. I can't really see chat here. What do you get? 160, okay? And what do you get when you multiply 160 by 16? So there you go. Make sense? You're already well on your way. Does everyone understand what happened? Ryan asked an excellent question. I'm very happy that he asked that question, and he was already able to answer it himself. Does everyone understand what happened? He asked, okay, what's the complementary resolution to 1440, right? And I asked him back what the aspect ratio is, right? Because those are complementary values. They go together. You must know the measurement of at least one side of the display, the one resolution or lines of resolution, one side of display, and you must know the aspect ratio. So what's the general, so give me some feedback in chat. Yes, do you understand? Does everyone understand what happened? He said, okay, what's the complementary ratio or resolution to 1440? I asked him the aspect ratio. He already immediately knew what I meant by aspect ratio. He picked an appropriate aspect ratio. 16 by 9, 16 by 10 are the most common. There you go, Ryan. It's good to be right, right? It's good to be able to be right on the answer to your own question. So outstanding, right? Ah, excellent question. Okay, why did we divide 1440 by 9 and not 1440 by 16? Because in my experience, right, 1440 is unlikely to be the width measurement of the display. It's very likely to be the height measurement of the display, right? So we talked a little bit earlier about our aspect ratio when I drew my rectangle, right? And we said that we had an aspect ratio of 16 by 9, right? 16 wide by 9 tall, right? And Ryan asked, okay, what about 1440? Okay, I'm gonna put it, well, you can't necessarily see chat at the same time, so I'm gonna put it in the screenshot here. Ryan asks, what about 1440, right? So we were just talking about 1080 as a common resolution. So it's, and we talked about the complementary size to 1080 is 1920, and he's talking about a newer type of display, a better type of display, right? So it's more likely that he's talking about a display that is denser in the vertical direction than in the horizontal direction, because that would actually be a downgrade if that was the horizontal measurement, right? Yeah, cross product, right? So he asked, what about 1440? So 1440 must indicate the vertical resolution, right? So if we have a 16 by 9 aspect ratio, then the common value between the two is going to be your 1440 divided by your height ratio, which gave us 160, right? Okay. And if the display has a 16 by 9 aspect ratio, then that means that the width is going to be the 160 that we derived times the 16 portion of the aspect ratio, which gave us the 2560 pixel width. So the overall resolution of a 1440 display, physical resolution is going to be 2560 pixels in width by 1440 in height. Does that answer your question, Euban? Both excellent questions.